I don't want you to be behind, so just bear with me if I sneeze or cough on the microphone. Now, just one or two announcements before we get started with chapter 3. Sorry, with chapter 8, before we get started with our lecture today. Regarding our, yes guys, ours gonna get harder. Yes, it's gonna get less time for you to solve it. Yes, this is how it's gonna be from now on. It's a lot more questions than before. Yes, it is more questions than before because this is the pace of the course. It's not me. It's the pace of the course that you signed on as you enrolled in. This course goes in a very fast pace. This is why I prepared for you the slides, ask you to print it out. I try my best to give you at least a week, 4 hours. Sometimes it doesn't happen because you'll be done from the chapter and starting another chapter and things like that. So please get used to this. Just for this time, and this is the first and the last time, I'm going to give an extension for our homework. The first and the last time. I'm going to give an extension till today. Oh, what's going on? I don't know. Okay, I'm going to give you an extension just because many of you were like so behind. They are even working. They worked after the deadline. I checked, and some of you are still working after the deadline. And that tells me that you wanted to do it, but maybe you run out of time. And I feel I don't want to kind of discredit you because you were after 12, and I see some people still working on that. Just maybe they're going to get some credit. So I'm going to do that for the first and the last time. I'm going to do it after this class. I'm going to give you an extension for hour till 11:59 tonight. Okay? If you did already, for those who were working after 12, if I'm going to give the extension, then it's going to be considered part of what you did. That you did the homework. The last time we were talking about acids and bases. We talked about what is the definition. An acid being an acid is something that gives a protein. Something like that is an acid. And we talked about the base, and that base has two definitions. The first definition that says like it's that a base is something that gives OH minus, like Na in here, like NaOH in here. Or the other definition of a base is by Brown-Stick-Lowry, and it is something that accepts a protein. So this is a base because it accepts a protein. Here, it's because it releases OH minus. So those two definitions are both definition of a base. It's by two different scientists. So and we get to the table that we talked about before when we were mentioning strong electrolyte, weak electrolyte. So this is, you need to know those because in a minute that's going to be so helpful, and you wouldn't be able to write the net ionic equation if you don't know the strong acids, strong bases, weak acids, weak bases. So those are the strong acids. You need to know those. You need to learn these. I'm not going to give you that in the exam, in exam 1. Those are the weak acids that you need to know also. And we're going to talk in a minute what is the difference between the two. Those are strong bases. And this ammonia is a weak base, and acetate is also a weak base. So that's it. Those are the strong acids, strong bases, weak acids, weak bases. Now we're gonna talk about what's the difference, how that's gonna differ when we talk about the net ionic equation, because the idea behind this is to get to the acid-base reaction. We're gonna talk about the acid-base reaction in a bit. So let's do this eye quicker about strong acids, strong bases before we go any further. Okay. Oops. I'm gonna stop it at 1 minute. Okay, I'm gonna stop it right here and check what you think. So I have 86% for BB is the right answer. So HCl, all the halogens are strong acids. The acids of halogens of group 7A are all strong acids except HF. It is a weak acid. So this is a strong acid. Acetic acid, which is vinegar, is a weak acid. HNO3 is a strong acid. And this is a strong acid. H2SO4 is a strong acid. So B is the right answer. Now, what is the difference? What are the differences between a weak acid and a strong acid? So a strong acid, like HCl, is an example of a strong acid. When I put it in water, that means it is aqueous. It dissociates totally into its ions. In other words, when I put this HCl in water, if I start with at t equals 0 with x mole of HCl, at the start I have 0 of this and 0 when I first put the material. At time t, at a certain time t, I'll have 0 HCl, x moles of H and x moles of Cl minus. That means all of the HCl gonna dissociate into its ions, into H plus and Cl minus. Okay? And this is what strong acids are. When you put them in water, they directly go all the material to H plus and Cl minus. And this is why it's a strong acid, because it's a change from HCl, which is a covalent bonding, into H plus, and this is the definition of an acid. It's something that gives H plus. So it gave all the H pluses. This is why it's a strong acid. This is the case for all the strong acids. When we put them in water, they dissociate into their ions. In other words, when I write it in the net ionic equation, if I have a strong acid, I'm gonna put it into its ions. Okay, let's see what is the case for a weak acid. Example, HFO. I'm going to start with HF. HF is a weak acid. When I put it in water, let's say I started with the same X moles, the same as HF at time 0. At time equals 0. If I come back and test the beaker and test the content of the beaker after a certain time, I would find an amount Z, and here I'm found Y. That means, in other words, just a partial, a small part of the HF gonna change into H plus. The other parts is gonna stay in the form of HF. So if I test the beaker, I'm gonna have some HF, mostly HF, a little bit of H plus, a little bit of F minus. Well, if I look to the beaker of HCl at time x, at time t, I'm going to find all of it H plus and Cl minus. And this is why HF is a weak acid, because it's given a tiny amount of it. Tiny amount of it will go to the H plus, which is the definition of an acid to go to H plus. This is the definition of the acid. If it doesn't go to H plus, it's not an acid. It's not a strong acid. So in other words, if I have HF in a net ionic equation, I wouldn't break it into H plus and F minus. I'll keep it as it is. Why? Because it's tiny amount of that goes to H plus and F minus. Very tiny amount. So whenever I have a weak acid in a net ionic equation, I'm going to keep it as it is, as if it is a precipitate or a solid. I don't break it into its ions. While for a strong acid in a net ionic equation, I'm going to break it into its ions. Does that make sense? Very good. Now, just I'm going to comment on, actually, let's go to the strong bases and weak bases. For the strong base, a definition of a base is something, of a strong base is something that releases an OH minus. So a strong base is something that's going to go to OH minus. So when I put NaOH, which is a water soluble, according to the solubility rule, it is a soluble hydroxide. If you go back to the table of solubility rules, it says that only for hydroxide, most hydroxides are insoluble except sodium, potassium, ammonium. Those are the soluble ones. So if I have a strong base, it is listed with the strong bases, and it is water soluble, it totally dissociates into Na plus and OH minus. The same idea as HCl, that when I put it in water, it dissociates. So after a time t, the only thing that I'm going to see in there is Na and OH minus. No NaOH inside the beaker. And this is why for strong bases that are water soluble, we can, in net ionic equation, we put them as, and we put their ions as a representation for them because they dissociate totally. Now, if we go, for example, to an example of copper hydroxide. Copper hydroxide, when I put it, it's a precipitate, it's a solid. When I put it in water, it can only, although it's a strong base, only a very tiny small amount of that go to copper 2 plus 2 OH minus. Very tiny amount. Although it's a strong base, but it isn't water soluble. So when I put it in water plus water, it's only a very tiny amount of it goes to its ions. This is why when I have copper hydroxide or any of those hydroxides that are listed on the table as non-water soluble, as insoluble in water, I don't break it into its ions, although it is a strong base. Although it's a very strong base. Now, for weak bases, we have ammonia as a weak base. So a weak base, when I put it in water, it's gonna slightly, by definition, a weak base is something that accepts a proton. This is why if I have a net ionic equation, I keep ammonia as it is, if there is no ions for ammonia. So this is why in a net ionic equation, I'm gonna keep it as it is. Okay. Okay. So now, do you need one more minute, guys? Okay. Now the whole idea of identifying what is a strong base, a strong acid, and all of this is to get to the point to discuss the acid-base reaction, which is mainly an acid with a base. We're gonna add them together and we're gonna see what we're gonna get. Usually whenever we add an acid to a base, we're gonna form a salt. Okay? Now let's say in here I have NaOH, which is a base, and it is a strong base, and HBr, which is a strong acid. So when I add them together, it's kind of the same as the precipitation reaction. They're gonna swap the anions, and if I swap the anions, I'm gonna have sodium bromide plus H2O. Usually, whenever an acid reacts with the base, it's gonna give us a salt plus water. There is an exception for that, which is a weak base with a strong acid or a weak acid, which we're gonna talk about. So usually whenever a base reacts, it's going to give us a salt plus water. The water is definitely liquid. NaBr is aqueous. We know that from the solubility rules. All sodiums are water soluble. Now, the idea is to go from this main reaction to the net ionic equation, the same as we did in the precipitate reaction. So your first step is to form those salt and water. Make sure that the formula is balanced. I know that sodium belongs to group 1, so it is Na plus Br minus belongs to group 7. So NaBr, the whole equation is balanced. Now I can go to the steps to the net ionic equation. The same way as we did in the precipitation reaction. So NaOH is a strong base and it is aqueous. So a strong base and it is aqueous, I'm going to break it into its ions. So it's going to be Na plus OH minus AQ. HBr, it is a strong acid. So I can break it into its ions in this net ionic equation. And NaBr, it's water-soluble salt, so I'm going to break it into its ions. Water, it's going to stay as it is, water liquid. And after that, I'm going to figure out what are the spectator ions, and I'm going to cancel them. I'm going to cancel those, so this one with this one, it's going to cancel. Br minus with Br minus is going to cancel. So my net ionic equation is whatever left there, which is OH minus aqueous plus H plus aqueous to give water liquid. Guess what? The reaction of any strong acid with aqueous, that's very important, with a soluble strong base, this is the net ionic equation. H plus OH minus to give H2O liquid, which is water liquid. This is the net ionic equation of a strong acid. There are conditions. It must be a strong acid with a strong base, and the base is water soluble. If the base is not water soluble, that's not going to be the case. Okay? So, what we're going to do is about 4 eye clickers. We're going to discuss the different, after the eye clicker, the different net ionic equation for different cases, a strong acid with weak base, with strong acid, and so on. Let's start with this one, with the first one. So I have KOH plus HCl. What is the net ionic equation? In every one of these, I'm asking what is the net ionic equation. So you need to follow the same steps. First, find out what is the chemicals that are produced, the products. Then think, is it a strong acid or a weak acid? If it is a strong acid, you're going to break it into its ions. If it is a strong water-soluble acid, you're going to break it into its ions. Then you're going to find the spectator ions. I'm going to stop it at 2 minutes, okay? Okay, let's see what the equation is. So I'm going to stop it right here. So I have 91% for BB is the right answer. So first of all, you have to identify, yes, this is a strong water-soluble base. How do I know that it is a strong base? Because it have an OH. Most inorganic compounds that have OH, they are strong bases. And then I go to the rules, to the solubility rules. KOH is water-soluble, so this is a strong water-soluble base. HCl or halogen, all the acids of halogens are strong acids except HF. So this is a strong acid. So it's going to give me KCl plus water. You can either do it the fast way, which is thinking, oh, it's a strong acid with a strong base, so definitely this is the net ionic equation, or do it in the slow way, which is then say, oh, that's going to go into its ion, and HCl, it's a strong acid, it's going to go into the ions. KCl is a water-soluble salt. Water is going to stay as it is. Now I'm going to cancel the spectator ions. So the net ionic equation is OH minus plus H plus aqueous to give water. Okay. Now let's go to another example. What is the net ionic equation for the reaction when acetic acid reacts with potassium hydroxide? Again, I'm going to stop it at 2. So I'm going to stop it right here and check what you think. So I have 61 for C. And yes, C is the right answer. So let's see how come C is the right answer in this case. So the first thing, this is a weak acid as it's listed there. So this is, I'm giving you different examples with different cases. So this is a weak acid, and that's a strong soluble base. So the only thing that is a little bit different in here when dealing with acetic acid, that this is the anion, and this is the cation, which is OH+. And this only happens with organic compounds, organic acids that have carbon, hydrogen, oxygen, carbon, hydrogen, sulfur. It must be carbon, hydrogen, something. That this is going to be now the anion, this is the cation. Because what we're used to, for example, HCl, it's always the H is the cation first. The cations comes before the anion. This is kind of an exception, which is organic acids. So what I'm going to do is swapping anions, keeping in mind that this is the anion. So I'm going to end up with KCH3CO2. H2 plus water. So it is the potassium acetate. And we know that potassium acetates are water soluble from the table, from the solubility table. So my next step is writing the net ionic equation. Acetic acid being a weak acid, I'm not going to break it into its ions. So I'm going to keep it as it is. Because only slight amount of that, when I put it in water, only slight amount go to H plus and acetate. Now KOH is a water-soluble strong base, so it's going to be K plus AQ plus OH minus AQ. This is a water-soluble salt, so in water it's going to its ions plus H2O liquid. Now I'm going to cancel those spectator ions, so I'm left with C and the net ionic equation. Okay? So this is the difference when weak acid, when strong acids react with a strong base, it is H plus OH minus give me water. In this case, no, it's different because I have a weak acid. Okay? So usually the rule, if you keep going with the rule that you don't break down the weak acids and the weak bases, you're gonna get it right all the time. Okay? Now let's go to another example. Again, I'm gonna give you 2 minutes.
What is it?
CU.
What is it? Is it one? Is it on the chart?
Okay, I'm gonna stop it right here. So I have B as 54%. B is the right answer. So first of all, this is a strong acid, and ammonia is one of 2 weak bases that we're gonna talk about in this whole course. So it's a weak base. Now the definition of a weak base that it accepts a proton. It takes an H plus, and it doesn't release OH minus. So in this case, we're not gonna form water because NH3 is not a strong base. It's just gonna accept a proton. So what's gonna happen that this H plus from the nitric acid, which is a strong acid, gonna be accepted by ammonia to give ammonium with a plus. So it's gonna be ammonium plus. And then the nitrate will be the anion. So this is going to be the cation now, and the nitrate is the anion. And this is an example. This is the example where when strong acids react with weak bases, they don't form water. They just form something like that. Now, in this course, we're gonna talk about only 2 weak bases. It's got a little bit more extensive. There is a more extensive list of weak bases when you go to organic chemistry, but those are the 2 that we're gonna know. So if you know those 2 examples, that would be great. Now, let's go to the net ionic equation. I know that this is water soluble from the solubility list. I'm going to break down the HNO3 into H plus and NO3 minus because it's a strong water soluble acid. Ammonia, I'm going to keep it as it is. Give me ammonium AQ plus NO3 minus AQ. I'm going to remove all the spectator ions, which NO3, NO3. So whatever left in there is the net ionic equation, which is B. Okay? Let's do one more. Again, I'm gonna stop it at 2 minutes.
See.
Okay. So I'm going to stop it right here and check what you did. Okay, so stop it. What's going on? Okay. So I have C as 53%. C is the right answer. Okay, let's see how come C is the right answer. So I have copper hydroxide plus HCl. Copper hydroxide is a strong acid, but unfortunately is insoluble in water. So when they're gonna react with each other, this not gonna go into slight amount of this gonna go to copper 2 plus and OH minus when I put it in water, very slight amount. This is why I'm gonna keep it as a solid when I'm writing the formula. Again, HCl gonna react with that, they're gonna swap the anions, so I'm gonna have copper chloride plus H2O. Okay? Now, second thing, I have to make sure that the equation is balanced. I have 2 chlorides, this is 2, so I have, now this is the equation is balanced. Okay, in all the other examples, it was balanced all the time because the cations have 1 plus as a charge. In this one, it's the cation, which is copper. It has a 2 plus as a charge. Do you know how did I know that it is 2 plus? So, that's liquid, that's aqueous. Now I'm going to go to the net ionic equation. Copper hydroxide, I'm going to keep it as it is because it is water insoluble according to the solubility rules. This I'm gonna break it into its ions. Now I have 2H plus and 2Cl minuses. Here I have copper 2 plus and I have 2Cl minuses. And I'm gonna keep it as it is. Okay, so what the only spectator ion is Cl minus, whatever left is the net ion. Okay, and I think this is the last examples about acid bases. These are the acid bases reaction. It's either a strong acid with a strong base, strong acid with weak base. It can be different acids, but it's exactly the same way. We're going to deal with it the same way every time. Now what we're going to get started with is the oxidation reduction reaction. So we covered the precipitation, we finished acid bases today, and we're going to begin to get started with the oxidation reduction reaction, which we usually refer to as redox reaction. Redox reactions. So redox or oxidation reduction is the same term. Now oxidation reduction reaction, the very old definition of oxidation reduction reaction is any process in which oxygen is added to another substance in an oxidation reaction. So the very old definition is if I'm burning wood and I'm forming, for example, carbon dioxide plus water, since I added oxygen to the carbon and oxygen to the hydrogen, that's an oxidation reaction. Magnesium, any metal with oxygen to form the oxide form of it, it is an oxidation reaction. It is an oxidation reduction reaction. But this kind of terminology or definition is the very, very old, the oldest definition of an oxidation reduction reaction. Now, the modern definition of oxidation reduction reaction is the process in which electrons are transferred from one compound to the other. Okay, so let's start first of all the redox reaction. So whenever there is reduction, there will be an oxidation taking place inside the beaker or within the two chemicals. You have to think about this as playing a game, or for example doing gambling or something. So if one lost, the other definitely win. If there is a winner, there is a loser. It couldn't be that you're gaining money, you're getting money from nowhere. You have to get the money from somebody. If someone wins, definitely there is a loser. This is why it is called redox reaction. There is a reduction and oxidation at the same time. Okay? Now, let's start with the oxidation. By the way, this is the most confusing part of this chapter because it has a lot of terminology and it's confusing. So, just concentrate as much as you can on the terminology as I go. So, oxidation is when a substance transfers or loses electrons. The substance is a reducing agent. So, let's start first. An oxidation reaction. So, oxidation reaction is the reaction where the substance or compound loses electrons. It can be 1 electron, 6, 7, it doesn't matter. It's not about 1 electron, it's losing electron. An example of that is this example. Let's say I have X, which is an element. It lost n electrons. It could be 1, 2, n is an integer. Then this is the most confusing part. So if X lost n electrons, it's going to have n plus as a charge. Remember, n plus doesn't mean gain. It means that it has a plus charge. It lost. It happens every semester that the student, because our mind is said that plus means gain. It's not the case in here. This is a charge. It doesn't mean that it gained 2 electrons or n electrons. Okay? So this reaction is called oxidation because the X lost electrons. Now, how are you going to keep in your mind what is oxidation, what is reduction? You can use this one, oil rig. So this use this. Oil means oxidation is losing. So if you forget what is losing, is it oxidation or reduction, use this. And reduction is gain. Okay? So, since this reaction, in this reaction, this X, the reactant lost electrons, it is an oxidation reaction. Now, the most confusing part is that if this is an oxidation reaction, this is a reducing agent. And I'm going to explain in a minute what does this mean. Okay? Okay, so if the reaction is oxidation, the reactant is a reducing agent. Okay, how come? Just imagine that also we're in a game, and let's say I'm the loser all the time. I'm the person, whoever I'm playing with, I'm the loser. I always lose. So that's an oxidation. Yet everybody, if anybody wanna win, they will play with me because I'm a reducing agent. I help everybody else win. Although I'm a loser, I always lose, but I'm a helping agent for everybody else to win. This is what it does. So if it is an oxidation reaction, it is a reducing agent. It helps the other element to get reduced, to gain. Okay? So this is the oxidation reaction. Now the reduction reaction is when substance accepts a proton, gains a proton, gains an electron, sorry. It gains an electron or electron. Okay? So in this one, while gained electrons, this is what's going to have N minus. And minus does not mean lost. It means that it have now more electrons in there. The reaction is called reduction reaction. And if the reaction is reduction, by default, the reactant is called an oxidizing agent. Okay. Now I just want to comment on both of the processes that I wrote or the reactions that I wrote. Now this is the most probable thing that X gonna lose. It's a neutral atom, it loses electrons, and it is N plus. Sometimes we may have, for example, X2 plus, and then we add 2 electrons, or it loses more, 2 electrons more, and it is X4 plus. It's not always going from a neutral atom to a charged one. And the same for this one, it could be Y, for example, 2 plus, and it gains 2 electrons, so it is a neutral. It's not always going from Y to N minus, and it's not always the case, but this is the most probable case that this is gonna happen. Okay? Now let's get started with a real example of oxidation reduction reaction. This reaction that we're gonna show it to you on Wednesday, we have a silver ion plus copper, which is copper is a solid, so I would have, you're gonna see it on Wednesday, I'm gonna have a beaker, and in the beaker I'm gonna have AgNO3. It's an aqueous, transparent or colorless solution. I'm gonna put the copper, which is a metal, inside it, and suddenly I'm gonna see that the Ag from the solution, the Ag plus of the solution, gonna deposit on that copper. And the copper and the solution gonna get together. We're gonna see that reaction. And what's going on is a redox reaction. As you can see here, the Ag is aqueous plus copper. It's giving me copper 2 plus plus Ag. Now let's break this reaction down. Let's start with the copper. I have copper solid going to copper 2 plus. So did copper solid lost or gained? Lost. How many electrons? 2. Okay. So what is this reaction? Oil rig. Oxidation is losing. X, so it is an oxidation reaction. Because oxidation is losing, the reactant lost, so it is oxidation. That implies copper is the reducing agent. Okay. Let's go because we said any oxidation there is reduction going on in the other part of the beaker. So I have 2Ag plus, and I went to 2Ag solid. Did it lose or gain? Gain. How many electrons? So it gained, if it is 1 Ag, it gained 1 electron. But because I put the stoichiometric coefficient there to be 2, so it gained 2 electrons. Since it is gaining, reduction is gaining, so this is a reduction reaction. That implies this is the oxidizing agent. Okay? Now, how we get to this equation? Usually we do those half reaction, we call them half reaction. Then we add them together such that the number of electrons cancels each other to get this one. Now, you're gonna learn in Chem 112 how to balance an oxidation reduction reaction, but not in this course. In this course, you're gonna get introduced how to know the oxidation number, and you're gonna know what is the oxidizing. You're going to be asked about what is the oxidizing agent, what is the reducing agent, is it an oxidation, is it a reduction. But in Chem 112, you're going to learn how to balance this equation. So let's do an eye click about that. I'm going to stop it at 1.
Yes.
Okay, so I'll stop it right at 120 and check what you see. So I have 67% for it, let's see. So I have Fe3 plus, and it's going to Fe2 plus. So it gained 1 electron. That implies gaining is reduction reaction. That implies this is the oxidizing agent. So that means Fe3 plus is the oxidizing agent. That means A is the right answer. Okay? Okay, so let's do. Okay, so what we're gonna do is I'm gonna stop right here, and we're gonna start with determining the oxidation number on Wednesday.